What would you see if the universe forgot to build stars around you? What would it feel like to drift in a place so vast and hollow that light itself seems to have given up? Can you imagine a void so immense, so unfathomably empty, that the very notion of existence feels like a myth? Close your eyes. Picture yourself floating alone in a super void, an immense sphere of darkness where the very fabric of the cosmos feels unfinished. There are no stars, no galaxies, no soft glow of clustered starlight to anchor your place in the universe. With the naked eye, or even the power of an amateur telescope, you see nothing. No Orion, no Andromeda, no comforting map of constellations we once used to navigate both oceans and imagination. To you, the universe would feel truly empty. And yet, this place exists. It is not fiction, but fact, known as the Boötes Void. This cosmic cavern spans 330 million light-years across a chasm so large, the Milky Way could vanish into it millions of times over. Despite its gargantuan volume, roughly 1 million cubic megaparsecs, where we would expect thousands of galaxies to cluster and dance in gravitational spirals, astronomers have observed a mere 60 galaxies scattered like whispers in the dark, faint spiral, and blue echoing the birth cries of young stars forming in isolation. Astronomer Greg Aldering once remarked that had the Milky Way formed within the center of this void, we would not have discovered the existence of other galaxies until the 1960s. That's how barren, how deceptively silent this region of the cosmos is. Imagine if Earth lay on one edge of this void. The light from the opposite side would only just now be arriving, carrying stories from a time when amphibians still crawled through primordial swamps, millions of years before even the first dinosaur opened its eyes to the sun. The Boötes Void, often called the Great Nothing, defies our expectations of cosmic structure. According to our understanding, the age of the universe places a strict limit on how large any coherent structure can be. No galaxy cluster, no cosmic filament, no void should exceed several tens of millions of light years in diameter. And yet here we are, confronted by a structure that shatters that threshold, a supervoid that challenges the very rules we thought governed the universe. Its presence tells us something, though. The few galaxies that do reside within it are not randomly strewn, but instead follow a linear, almost tubular pattern. It is as if we are seeing the fragmented ruins of a wall, a cosmic boundary crumbled between two adjacent voids. Individually, these voids make sense, but collectively, they form a structure beyond what cosmic evolution alone should allow. Even in this cosmic abyss, this supposed great nothing matter still finds a way to cling to structure, light still finds a way to be born. Yet to glimpse true darkness, to peer into the deepest recesses of time and space, we must look beyond even the Boötes Void. We must travel not just across distance, but backward through time, to an epoch before stars, before galaxies, before light itself. This is the era cosmologists call the Cosmic Dark Ages. For nearly 200 million years after the Big Bang, though the universe possessed all the raw ingredients needed to forge stars, no star had yet ignited. There was no light, only cooling hydrogen-helium and the silent seeds of future galaxies. The darkness was not metaphorical, it was literal, total, and enduring, a silence so absolute that the cosmos itself seemed to be holding its breath. And so we must ask, why did the universe wait so long to turn on the lights? What does this long, unilluminated pause reveal about the galaxies we see today? How can we possibly understand an era where there was no light to guide us? From Copernicus, who displaced the Earth from the center of the solar system, to Hubble, who revealed our galaxy to be one among billions, the history of cosmology has been a series of humbling revelations. We are not the center of anything, not the solar system, not the galaxy, not even the universe. The deeper we look, the more we realize how small our place is and how vast the mystery still remains. The Edge of Darkness, observing the threshold between light and night. In the annals of observational cosmology, few moments have marked a turning point as sharply as the Hubble Deep Field exposure of 1995. This historic event did not begin with grand discoveries or triumphs, but rather from skepticism, pressure, and a bold scientific intuition. The Hubble Space Telescope, the crown jewel of astronomical instrumentation, had endured a tumultuous debut. Its launch into low Earth orbit had been met with both optimism and public scrutiny, amplified when the first images returned from space were far from the clarity scientists had anticipated. Despite Hubble's mirror being one of the smoothest and most precisely ground optical surfaces ever created, a minuscule aberration less than 1/50th the width of a human hair resulted in devastating image blur. The collected photons failed to converge accurately, and the telescope's great promise seemed to unravel into failure. However, Hubble's low Earth orbit, which could have been a logistical limitation, became a saving grace. A crude servicing mission by NASA astronauts was able to correct the flaw through an ingenious optical fix, a series of small corrective lenses, not unlike those in a pair of glasses. With its vision restored to sharpness, Hubble was back in the game, but its credibility still needed defending. Under political pressure and scientific expectation, Robert Williams, the then director of the Space Telescope Science Institute, was allotted discretionary observing time hours. He could spend observing anything in the cosmos. What he chose shocked his peers. Rather than direct Hubble's unprecedented sensitivity toward a known target, a star-forming region, a prominent nebula, or a supernova remnant, Williams decided to point the telescope at what was effectively nothing. A tiny, seemingly empty patch of sky in the northern hemisphere covering an area no larger than 1/30th. The diameter of the full moon was selected. To the human eye and to all previous telescopes, it was devoid of structure or light. There were no visible stars or galaxies. It was a celestial void. For 10 continuous days, Hubble gazed at this darkness. With each passing hour, its deep field camera gathered the feeble ancient photons arriving from the farthest recesses of the universe. This act of patience and vision culminated in the Hubble Deep Field, a single image that contained thousands of galaxies, each a sprawling collection of billions of stars suspended in space and scattered across time. It was an astronomical revelation. What had once seemed like emptiness was in fact a dense thicket of galactic forms, spirals, ellipticals, irregulars, red, blue, and everything in between. But this image was more than just a cosmic census. It was a temporal map. Every point of light captured was not only distant in space, but also in time. Due to the finite speed of light, observing faraway galaxies is equivalent to looking into the deep past. The farther away the galaxy, the longer its light has traveled, and the further back in time we are observing. Some of the galaxies in the Hubble Deep Field appeared as they were billions of years ago, close to the time when galaxies first began to form. To interpret this phenomenon with rigor, cosmologists conceptualize the observable universe as a set of concentric spherical shells centered on the observer. Each shell represents a greater light travel distance and therefore an earlier epoch. The light from our sun takes approximately 8 minutes to reach us, placing it in our innermost shell. The light from the Andromeda Galaxy, our nearest galactic neighbor, takes about 5 million years, carrying with it the image of that galaxy as it existed when early hominids like Homo habilis roamed the Earth. This ladder of light time continues outward. With advanced telescopes like Hubble and now James Webb, we can peer out to shells whose light began its journey just a few 100 million years after the Big Bang. These earliest visible galaxies, little more than red smudges, are some of the universe's primordial stellar systems. As feeble as these signals are, modern instruments allow us to dissect their light using spectroscopy. The same principles that govern the Doppler shift of a passing ambulance's siren apply to light. When a galaxy recedes from us, its emitted light stretches into longer wavelengths, a phenomenon known as redshift. Chemical elements emit light at known frequencies. When we observe their spectral lines shifted into the red end of the spectrum, we can quantify how fast the galaxy is moving away. Edwin Hubble, whose work underpins modern cosmology, famously discovered that the farther a galaxy is, the faster it is receding. This empirical relationship became foundational to the Big Bang model. In this way, redshift becomes a tool not only for measuring distance, but also for ordering galaxies chronologically. As we analyze deep field images, we are peeling away the layers of cosmic history, eventually arriving at the first luminous structures to emerge after the dark birth of the universe. The most recent deep field images from the James Webb Space Telescope offer an even sharper look into this past a single frame, covering a region of sky the size of a grain of sand, reveals thousands of galaxies, many dating back to a few 100 million years after the cosmic beginning. Yet there is a limit, a frontier beyond which even our most sophisticated instruments cannot penetrate. This is not merely a technological boundary, it is a fundamental limit of physics. Beyond a certain point, we arrive at a time before stars had ignited, before galaxies had formed, before there was any visible light at all. We call this epoch the Cosmic Dark Ages. To understand this profound darkness, one must return to the early radiation-dominated universe. Immediately following the Big Bang, the cosmos was a seething plasma of photons, electrons, and baryons. Light could not travel freely as it constantly scattered off free electrons, keeping the universe opaque. This state persisted until about 380,000 years after the Big Bang, when the universe cooled sufficiently for electrons to combine with protons and form neutral hydrogen atoms, a period known as recombination. With fewer free electrons to scatter photons, the universe became transparent for the first time. The radiation released at this moment, the cosmic microwave background, still bathes the universe today. However, although photons were now free to travel, the light emitted during recombination has been redshifted by the expansion of the universe. Originally a warm orange glow, it gradually stretched into the infrared and now into the microwave range. The universe cooled and visible light disappeared. The cosmic embers of creation dimmed into darkness. For nearly 200 million years, the universe entered a period devoid of any sources of visible light. The matter was too diffuse and too cool for nuclear fusion. There were no stars, no galaxies, and thus no new light. During this long night, another invisible actor played a critical role: dark matter. First identified indirectly by Vera Rubin and Kent Ford in the 1960s, dark matter's gravitational influence was needed to explain the unexpectedly high orbital velocities of stars within galaxies. According to Newtonian physics, stars orbiting at great distances from the galactic center should move more slowly. Instead, observations revealed that they maintained high speeds, implying the existence of unseen mass exerting additional gravitational pull. This mass, which does not emit, absorb, or reflect light, was termed dark matter. It is now estimated to comprise about 80% of the universe's total matter content. The behavior of dark matter is profoundly different from that of ordinary baryonic matter. while normal matter interacts through both gravity and electromagnetism, allowing it to cool by emitting radiation. Dark matter interacts only via gravity. This means that as dark matter collapses under its own gravity, it cannot radiate away thermal energy. Without this cooling mechanism, gravitational contraction is arrested when the pressure from random thermal motion balances the inward pull of gravity. Consequently, dark matter structures form vast diffuse filaments and halos but never condense into stars or planets. During the cosmic dark ages, dark matter formed a hidden skeleton upon which the future large-scale structure of the universe would be built. The absence of visible light does not imply the absence of structure. The dark matter filaments formed a complex cosmic web with nodes of high density, forming halos into which baryonic gas would later fall. These halos provided the gravitational wells necessary to accumulate and compress gas, setting the stage for the first stars. But for this to happen, the gas itself had to cool, condense, and eventually trigger fusion. Unlike dark matter, normal gas clouds can cool through atomic interactions. As atoms collide, electrons become excited to higher energy levels. When they relax back to their ground states, they emit photons, carrying away energy and reducing the internal pressure. Over time, this radiative cooling allows the cloud to collapse further, increasing in density until the conditions for nuclear fusion are achieved. In this way, the first stars, known as population 3 stars, were born. These stars were likely massive, short-lived, and composed almost entirely of hydrogen and helium, lacking the heavier elements synthesized by later generations of stars. Detecting these primordial stars directly remains one of the most elusive goals in astrophysics. Their faintness, great distance, and short lifespans conspire to hide them from even our most sensitive telescopes. Nevertheless, their indirect fingerprints may yet be found in the chemical composition of later stars, in the rayonization history of the intergalactic medium, and in the subtle distortions they imprint upon the cosmic background light. And so we return to the present. Our telescopes stationed above the Earth's atmosphere, armed with mirrors and spectrographs, continue to gaze into the void, not out of despair, but out of curiosity. The darkness is not empty, it is filled with structure, with memory, with signals stretched thin by time and space. From the glowing fog of recombination to the cool embers of the cosmic microwave background, from the hidden scaffolding of dark matter to the first glimmers of starlight, the universe reveals itself not in brightness but in persistence. As we trace the universe backward, peeling away the layers of time, we approach a limit beyond which no light was ever cast. And yet the questions persist. How did the universe first ignite? What mechanisms seeded the galaxies and clusters? We now see what lies beyond the observable horizon. These questions remain unanswered but not unreachable. The edge of darkness is not the end of knowledge, it is the beginning of insight. It is the place where physics, imagination, and the hunger for understanding converge, where the silence of the cosmos speaks in wavelengths too faint to hear, but whose message is clear. Keep looking. The hidden universe, illuminating cosmic darkness through hydrogen's whisper. On the afternoon of May 6, 1937, an enormous symbol of engineering pride and technological ambition descended toward its mooring mast in Lakehurst, New Jersey. The German airship Hindenburg, a leviathan of the skies and a marvel of intercontinental air travel, suddenly erupted into flames. The hydrogen that lifted it, a gas prized for its lightness, ignited with terrifying speed, engulfing the vessel in a fiery inferno witnessed by horrified onlookers. Though most on board survived due to the airship's proximity to the ground, the tragedy spelled the end of the hydrogen-fueled airship era A simple element, hydrogen, composed of one proton and one electron, had unleashed catastrophic energy when given the right mix of air and a spark of ignition. This elemental simplicity is deceptive. Hydrogen is odorless, invisible, and under the right conditions, violently reactive. In the case of the Hindenburg, the combustion of hydrogen ended an age of flight. But the power contained in the atom is not limited to chemical combustion. In nuclear physics, it serves as a gateway to vastly greater energies. The detonation of atomic bombs in Hiroshima and Nagasaki illustrated the terrible potential of fission. But the true apex of destructive energy lies in hydrogen fusion. Thermonuclear weapons based on the fusion of hydrogen nuclei, far more powerful than fission bombs, have only been tested in controlled detonations, never unleashed in war. Ironically, the same scientific curiosity that unlocked the hydrogen bomb also illuminated the stars. Many physicists who developed nuclear weapons were simultaneously probing the processes that power the cosmos, and it was hydrogen again that held the key. Yet while hydrogen's role in stellar fusion and weaponry occupied some minds, a quieter revolution was unfolding within astronomy. The focus of this revolution was not devastation, but discovery. John Oort, a preeminent Dutch astronomer, had already revolutionized our understanding of the Milky Way by showing that the Sun was not its center, but merely a peripheral resident located about 30,000 light-years from the galactic core. His work had confirmed that the Milky Way rotated like a massive spiral, and he became one of the most respected figures in the field. But by the early 1940s, war had disrupted European science. Oort, having protested the Nazi regime's dismissal of his Jewish colleagues, retreated from public academic life. Yet in isolation, he was not idle. The need to understand the true shape and extent of our galaxy continued to stir his scientific instincts. Oort's challenge was formidable. The Milky Way is a dusty system. Optical telescopes, which rely on visible light, are significantly hampered by interstellar dust that absorbs and scatters light. A comprehensive map of our galaxy would require seeing through this veil. The solution, Oort believed, lay in detecting radio waves, which possess much longer wavelengths and are largely unaffected by dust. But for this to work, the interstellar medium, the gas and plasma filling the galaxy, would need to emit radio signals detectable by Earth-based instruments. A breakthrough came in the form of a smuggled issue of the Astrophysical Journal that described potential methods of detecting radio emissions from space, or realized that hydrogen, which made up most of the interstellar medium, might provide the signal he sought. But the emission would need to be both widespread and physically plausible to detect. He tasked his student Hendrik Christoffel van de Hulst with identifying a suitable spectral line from hydrogen-1 that could serve as a beacon in the radio domain. Van de Hulst approached the problem with diligence, exploring the quantum mechanical behaviors of the hydrogen atom. In quantum terms, even the hydrogen atom's simplest structure harbors complexity. While most transitions involve electrons leaping between discrete energy levels, there exist subtler transitions hidden within those levels. One such transition is the hyperfine spin-flip transition. In this phenomenon, an electron orbiting a proton changes its spin orientation from parallel to anti-parallel. The energy difference between these two configurations is minute but real. When an electron flips to the lower energy state, it emits a photon with a frequency of precisely 14204 Hertz, equivalent to a wavelength of 21 centimeters. This emission lies firmly within the radio band, making it an ideal target for radio astronomy. Van de Hulst published his theoretical prediction in 1944, suggesting that this 21 centimeter hydrogen line could revolutionize our understanding of the Milky Way. The challenge, however, was daunting. The spin-flip transition is extraordinarily rare. The spontaneous transition of a single atom may occur only once in several million years. To detect such a faint signal would require immense quantities of hydrogen, far more than anyone had yet confirmed in the galaxy. Skepticism was understandable. Many doubted that the universe held enough neutral hydrogen to make the 21 centimeter line detectable at all. Nevertheless, Oort pressed on. Using salvaged components from wartime German radar equipment, he attempted to build a radio detection system, but he was no electrical engineer and the project stalled. Meanwhile, across the Atlantic, a team at Harvard, led by physicist Edward Purcell, had independently read Van de Hulst's paper and taken a keen interest. Purcell, whose background lay in nuclear magnetic resonance, saw an opportunity to apply his expertise in radio detection. He enlisted his graduate student Harold "Doc" Ewan, whose knowledge of radar technology proved crucial. Ewan constructed a horn antenna, essentially a hollow metal structure shaped to direct radio waves into a receiver using basic materials, copper-plated plywood, and campus electronics. This antenna, installed through a fourth-floor laboratory window, became the first successful apparatus to detect the elusive 21 centimeter line on a quiet Easter morning in March 1951. The experiment worked. A distinct spectral line at 1420 mmHz was observed, proving the existence of vast hydrogen reservoirs in the Milky Way. News of the success quickly reached Europe, and a collaborative scientific dialogue was born. The Americans shared the technical expertise needed to construct and calibrate radio receivers, while the Dutch provided the astrophysical framework that made sense of the findings. This transatlantic partnership catalyzed the field of radio astronomy, allowing astronomers to build detailed maps of hydrogen distribution throughout the galaxy. More than that, they could now measure not only where the gas was, but also how it was moving. By examining the redshift and blueshift of the 21 centimeter line, astronomers could determine the radial velocities of hydrogen clouds. These observations confirmed that the Milky Way was a rotating spiral with arms that could be traced far beyond the reach of optical light. The implications for galactic astronomy were profound, but the significance of the 21 centimeter line extends far beyond our local spiral. The same principles can be applied on cosmological scales. Hydrogen was the most abundant element produced in the Big Bang, forming the vast majority of normal matter in the early universe. Before galaxies, before stars, before planets, the universe was filled with diffuse clouds of neutral hydrogen gas. Much of this gas still exists today, and the hyperfine transition remains a tracer of its distribution. In particular, the 21 centimeter line offers a window into one of the most enigmatic periods of cosmic history, the cosmic dark ages. After the universe became transparent, following recombination, roughly 380,000 years after the Big Bang, there were no luminous objects to emit visible light. The photons from recombination gradually redshifted into the microwave regime, becoming the cosmic microwave background. For hundreds of millions of years, the universe remained dark in the optical spectrum, filled with hydrogen gas and dark matter, but devoid of stars. Yet, even during this period, structure was forming. Dark matter, which interacts gravitationally but not electromagnetically, began to collapse into filaments and halos. The baryonic hydrogen gas followed, drawn in by gravity, settling into the gravitational wells created by dark matter. As these gas clouds cooled and contracted, the conditions for star formation began to emerge. But to the human eye or any optical telescope, this process was invisible. The universe was still dark. Herein lies the power of the 21 centimeter line. Unlike light from stars which did not yet exist, the spin-flip transition of hydrogen could still occur. While individually rare, The sheer volume of hydrogen in the early universe ensures that the signal, when observed across cosmic distances, becomes statistically significant. By tuning radio telescopes to the redshifted 21 centimeter line, astronomers can detect the distribution of hydrogen across different epochs, tracing the evolution of matter long before the first starlight. Modern radio telescopes, such as the Square Kilometer Array under construction, are designed to take advantage of this fact. They aim to create three-dimensional maps of hydrogen distribution, effectively watching the universe evolve from darkness to light. These observations will not only pinpoint the locations where the first stars formed, but also help refine models of cosmic inflation, dark matter behavior, and the initial conditions of structure formation. The 21 centimeter line, then, is more than a spectral signature. It is a cosmic thread linking the present to the past, the luminous to the unseen. Through it, we can observe the quiet gathering of matter during the Dark Ages, when the universe was laying the scaffolding for galaxies, stars, and ultimately life. In retrospect, the hydrogen atom, simple though it may be, has proven to be one of nature's most eloquent storytellers. From the fiery destruction of an airship to the ignition of thermonuclear reactions, from the blazing cores of stars to the near-silent whisper of spin-flip transitions, hydrogen reveals itself across every scale. It is the most ancient of elements forged in the first few minutes of the universe, and it remains our most powerful tool for deciphering the cosmos. And so the universe was never truly dark. It was simply speaking in a different language, one that required new instruments, fresh insight, and a longer wavelength. The 21 centimeter line was the translator, the beacon, the whisper in the silence. Through it, we continued to learn that even in the deepest void there is form. In the darkness there is structure. The hidden universe is not empty. It is waiting to be heard. Let there be light, reconstructing the universe's path out of darkness. The deep ocean, Earth's largest and most enigmatic habitat, provides us with a terrestrial analogy for the cosmic darkness that once enveloped the early universe. As one descends beneath the sunlit surface of the sea, the light diminishes with increasing depth. At just 10 meters, the warm hues, reds, oranges, and yellows are absorbed, rendering the underwater world increasingly blue and green. By 50 meters, much of the visible spectrum has been swallowed by water, and the world is cast in an eerie monochrome. At 200 meters, one enters the twilight zone, a realm populated by bioluminescent creatures that have evolved to generate their own light. By 300 meters, one is immersed in the ocean's true darkness, an environment hostile to human perception yet teeming with life, adapted to this lightless realm. The metaphor is apt, for the early universe too was a place of darkness, not devoid of activity, but veiled from our visible senses. In the cosmic timeline, a similar descent into darkness followed the initial brilliance of the Big Bang. After the universe cooled from its initial hot plasma state and atoms formed during recombination, the cosmos entered a prolonged period of darkness. This era, known as the Cosmic Dark Ages, lasted for hundreds of millions of years. During this time, the universe was devoid of luminous sources, no stars yet shone, and no galaxies yet burned. And yet, like the deep ocean, the darkness was not synonymous with emptiness. Invisible to the human eye and to optical telescopes, the universe was already undergoing gravitational assembly beneath the shroud of blackness. The architecture of structure formation had already been laid. The gravitational influence of dark matter had begun to assemble filaments and halos, forming a vast cosmic web into which neutral hydrogen comprising the bulk of ordinary matter began to accrete by approximately 200 million years after the Big Bang. These dense hydrogen pockets had collapsed under their own weight to the point where fusion could be triggered. In doing so, the first stars ignited, and with them the first starlight broke the cosmic darkness. From every direction across the expanding cosmos, the first sources of light flickered to life. These were likely massive, short-lived population 3 stars, composed almost entirely of hydrogen and helium and devoid of heavier elements. Yet despite their brilliance, these early stars were not immediately able to flood the universe with light. The space between stars remained filled with vast amounts of neutral hydrogen, which readily absorbed specific wavelengths of radiation, particularly in the ultraviolet and optical bands. Much as ocean water absorbs light in the red and blue wavelengths, the surrounding hydrogen gas acted as an opaque veil that muffled the newborn light. An observer at this time might witness stars shining, but with their light dimmed and scattered, their spectra marred by characteristic absorption lines, specifically the Lyman alpha transition, and others where hydrogen absorbs at well-known visible wavelengths. The effect would not have been a total darkness, but a spectral tinting light filtered and shaped by its medium. The appearance of light did not therefore signal an immediate end to the Dark Ages. Rather, it marked the beginning of a new cosmic transformation, the epoch of Rayonization. During this epoch, the ultraviolet radiation from the first stars and later from the first galaxies began to ionize the neutral hydrogen that pervaded space. To understand this process, it is important to recall the atomic physics of hydrogen. In the Bohr model, the hydrogen atom consists of a proton orbited by an electron. When a photon carrying energy equal to or greater than 136 electron volts interacts with this atom, it can ionize it, freeing the electron from the proton and converting the atom into an ionized plasma. Following the Big Bang, the universe was too hot for neutral atoms to exist, and all matter was in the form of plasma. It was only after cooling for hundreds of thousands of years that electrons and protons combined to form neutral hydrogen, ushering in the Dark Ages. Now, with the advent of the first stars' photons with energies exceeding the ionization threshold began to reverse this process. Each luminous source created a local bubble of ionized hydrogen, a transparent region through which light could travel more freely. Initially, these bubbles were isolated and surrounded by darkness, but over time, as more stars and galaxies formed, the bubbles expanded, began to overlap, and eventually percolated through the intergalactic medium, transforming the universe from opaque to transparent once more. This global reionization of the universe was not the result of individual stars alone. Although population 3 stars contributed to the early phases of rayonization, their short lifespans and limited ionizing output suggest they could not have completed the process alone. Instead, it was the first galaxies harboring longer-lived population 2 stars' massive star-forming regions and potentially active galactic nuclei that provided the sustained ionizing radiation necessary to reionize the cosmos. By about 1 billion years after the Big Bang, the rayonization process was largely complete, and the universe became once again transparent to ultraviolet and visible light. Photons could travel across vast distances without being absorbed, and the large-scale structure of the universe could be observed in the way we experience it today. However, the details of this transformation remain elusive. The Dark Ages and the epoch of reionization represent a missing chapter in the cosmic narrative. A few galaxies from this time have been observed, dim ancient sources detected at extreme redshifts, but they are sparse to reconstruct a coherent picture of this era. From such a thin sample would be like reconstructing all of human history from a single archaeological artifact found every few centuries. The desire to peer into this mysterious epoch was a primary motivation for the development of the James Webb Space Telescope, launched on December 25, 2021. Whereas the Hubble Space Telescope operates primarily in the optical and near-infrared bands, JWST was designed to probe much further into the infrared. This distinction is critical due to the expansion of the universe. Light from distant galaxies is redshifted, its wavelength stretched such that photons originally emitted in the ultraviolet or optical range arrive at Earth in the infrared. Hubble's instruments, while powerful, are limited in their ability to detect these heavily redshifted signals. JWST, by contrast, can detect galaxies whose light has redshifted entirely out of the visible spectrum. Within its first year of operation, JWST succeeded in detecting some of the most ancient galaxies ever observed, with estimated formation times just 350 million years after the Big Bang. Yet even JWST has limitations. While it can observe further than any previous telescope, its field of view is small and its resolution constrained by its mirror size. Moreover, it is not equipped to see the earliest stages of the Dark Ages or to map the reionization process in its full complexity. To push further to capture the moment when the first hydrogen atoms were reionized, we must turn to an entirely different part of the electromagnetic spectrum, the radio band. As we journey backward in time, observing galaxies at ever greater redshifts, we simultaneously confront a paradox. The farther we look, the more of the universe we see per unit of sky area. But the lower our spatial resolution becomes, individual stars and even individual galaxies vanish into the statistical noise of unresolved light. To see structure on these large scales, we must observe phenomena that are spread broadly across space and time. This is where the 21 centimeter line predicted by Van der Hulst and discussed earlier becomes essential. As described, the 21 centimeter hyperfine transition of neutral hydrogen occurs when the spin orientation of the electron and proton in a hydrogen atom change from parallel to anti-parallel. This transition releases a photon in the radio part of the spectrum with a wavelength of 21 centimeters and a frequency of 1420 MHz. Though rare, the immense quantity of neutral hydrogen in the early universe makes this transition statistically significant over cosmic volumes. Critically, the presence or absence of the signal can trace the progress of reionization. In regions where hydrogen remains neutral, the 21 centimeter emission persists, but in ionized regions where electrons and protons no longer form bound atoms, the signal disappears. Thus, during reionization, the universe begins to resemble a cosmic Swiss cheese, with neutral hydrogen representing the solid structure and ionized bubbles representing the holes. By mapping these patterns, astronomers can infer the size, shape, and evolution of the ionizing sources, be they first stars, galaxies, or black holes. The signal offers a three-dimensional view of the invisible universe, providing not only spatial but also temporal information thanks to the redshift dependence of the wavelength. Detecting the 21 centimeter signal from the epoch of reionization is one of the most ambitious goals in contemporary astronomy. The challenges are formidable. The signal is faint, so faint that it is overwhelmed by radio noise from our own galaxy, from Earth-based sources, and even from distant quasars. Extracting the 21 centimeter signal requires instruments of unprecedented sensitivity situated in radio quiet zones and equipped with advanced signal processing algorithms. Projects like Hera-Lofar and the upcoming SKA are designed specifically to overcome these challenges. Their success will provide a definitive timeline of reionization, reveal the properties of the first light sources, and perhaps even detect primordial black holes. And so the phrase, "let there be light," acquires new meaning in the cosmological context. The universe did not flip a switch from darkness to illumination, rather it transitioned gradually through complex, overlapping processes. Light was born, struggled to escape, and slowly carved paths through the opaque hydrogen fog. The first stars kindled the cosmic dawn, but the light they emitted was absorbed, reprocessed, and shaped by their environment. Only after 1 billion years of growth, radiation, and transformation did the universe become transparent once more. Even now, we are only beginning to uncover the full extent of this transformation. The Dark Ages and the Epoch of Rionization remain a frontier in our understanding, an interval that shaped everything that followed, yet still shrouded in mystery. But with every new instrument, every new signal, we peel back the layers. We listen for hydrogen's whisper in the radio spectrum, decode its interaction with early starlight, and search for the moment when the cosmic night began to fade. And so we ask, is it truly possible to find the signal of rionization and illuminate the Dark Ages? The answer lies not only in better telescopes, but in our persistent curiosity. For even in darkness, the universe leaves traces. And when we tune our ears to the right frequencies, we find that the cosmos was never silent. It was always preparing to speak. The signal listening to the universe's silent dawn. Imagine yourself standing under the searing sun in the heart of the Australian outback. All around is a parched and ancient landscape, an expanse of ochre earth punctuated by sparse, withered vegetation. The air shimmers with dry heat. No rivers flow, no clouds break the sky. Yet this land, seemingly inhospitable to humans, sustains other forms of life. Sheep graze quietly. Cattle meander across the dust. They inhabit this terrain differently, not just physiologically, but perceptually. For them, this land is not the red and gold of our human vision, but a landscape shaped by different wavelengths of light, processed by different kinds of eyes. Biological vision systems vary dramatically across the animal kingdom. Humans with our red, green, and blue cone cells perceive the world in a narrow slice of the electromagnetic spectrum, what we call visible light. But this is only a fraction of what exists. Cattle and sheep lack the ability to detect red entirely. Snakes, though color deficient, can sense infrared radiation, a capacity that aids them in tracking warm-blooded prey. Scorpions, astonishingly, can both detect ultraviolet light and fluoresce under its illumination. Nature is filled with such diverse perceptual tools. Unlike any other species, however, humans have transcended our biological limitations by constructing artificial extensions of our senses. In mimicking nature's diversity of perception, we have invented instruments that detect ultraviolet, infrared, X-ray, and critically radio waves. In doing so, we did not simply build new tools of perception, we developed entirely new modes of communication. What began as terrestrial radio, an attempt to broadcast sound and images, quickly became something far more profound. By accident and intention, we began detecting the faint whispers of the universe itself. In the process, a new discipline was born, radio astronomy. By tuning our instruments to the longest wavelengths of the electromagnetic spectrum, we began to detect radiation, not just from other rooms or cities, but from planets, stars, galaxies, and the earliest moments of cosmic history. It was through these technological eyes that humanity found its way into the electromagnetic realm, otherwise inaccessible to biological life. It is deep in the Australian outback, one of the quietest radio environments on Earth, that one of the most consequential developments in the study of the early universe unfolded. Here, far from the noise of cities in the Murchison region of Western Australia. A desert covering nearly 50,000 square kilometers, with only about 100 inhabitants. A seemingly unassuming radio antenna detected something extraordinary. The instrument known as EDGES stands in stark contrast to the massive dishes and gleaming optics we typically associate with astronomy. It is a modest ground-based radio antenna designed to do one thing: detect the red-shifted 21-centimeter signal from neutral hydrogen gas that pervaded the early universe during the cosmic dark ages and the subsequent epoch of rionization. These hydrogen atoms formed after recombination and before the ignition of the first stars emit radiation at a characteristic wavelength of 21 centimeters, due to the hyperfine transition of the hydrogen atom's ground state. But as the universe expanded, these photons were stretched, redshifted, so that today they arrive at Earth with wavelengths between 1 and 2 meters, depending on their origin epoch. EDGES was designed to detect these photons not by imaging them as a traditional telescope would, but by measuring their collective brightness. Temperature, a global signal that provides an averaged view of hydrogen gas across cosmic time. It listens passively, its human operators often hundreds or thousands of kilometers away. The experiment operates like a celestial thermometer, scanning across radio frequencies to search for faint spectral dip signatures of interaction between hydrogen and the earliest radiation sources. In 2018, EDGES made a startling announcement. After years of careful calibration, noise modeling, and data analysis, the team reported the detection of an absorption feature at a frequency corresponding to redshift 17, or roughly 180 million years after the Big Bang. This detection, if confirmed, would mark the earliest direct evidence of the first stars, a cosmological milestone tantamount to discovering a birth certificate for stellar light. However, the implications of the signal extended beyond its timing. The depth of the absorption feature was twice as large as predicted by any standard cosmological model. In essence, the signal suggested that the hydrogen gas of the early universe was significantly colder than existing theory allowed. The discrepancy sent shockwaves through the cosmology community. At the heart of the puzzle lay the physics of the 21 centimeter line. The absorption of background photons at this wavelength depends on the spin temperature of hydrogen, which in turn is influenced by the kinetic temperature of the gas and the radiation field present. A deeper absorption trough implies that the hydrogen was either much colder than expected or that the background radiation field was much brighter. Both possibilities were unanticipated. One line of interpretation suggested a radical solution. Perhaps dark matter, long assumed to be non-collisional and thermally inert, could interact, however weakly, with normal baryonic matter. In this hypothesis, collisions between dark matter particles and hydrogen atoms would transfer kinetic energy, cooling the gas beyond standard expectations. If true, this would represent a fundamental shift in our understanding of dark matter with profound implications for particle physics and cosmology. The possibility electrified the field, but scientists proceeded with caution. Extraordinary claims demand extraordinary evidence, and the sensitivity of the EDGES experiment made it susceptible to contamination from terrestrial and galactic radio noise. The signal detected was incredibly faint, many orders of magnitude weaker than foreground radio emissions from our own Milky Way galaxy. Extracting the desired signal required complex modeling and subtraction techniques. Could the observed dip be a result of unmodeled instrument noise? Was there an unrecognized astrophysical foreground? Was it an artifact of calibration? To verify the result, independent confirmation was essential. A range of follow-up experiments soon emerged. In India, the SARAS experiment placed an antenna on a floating platform in a lake to minimize ground reflections and environmental noise. Its analysis, however, failed to reproduce the deep absorption feature reported by EDGES. While SARAS did not conclusively disprove the detection, its inability to corroborate it cast doubt. The field, always driven by data, began to retreat from the more exotic interpretations. The initial theories invoking dark matter-hydrogen interaction gave way once again to methodological scrutiny. Perhaps the signal was a systematic artifact, or perhaps the models of galactic foregrounds were insufficient. The return to conservatism was not defeat, it was scientific self-correction. And yet the potential insight gleaned from even the possibility of the EDGE's result had already reshaped priorities in observational cosmology. Despite the controversy, EDGE's had achieved something critical. It had galvanized the global scientific community to take the 21 centimeter cosmological signal seriously. Across the Murchison outback, other instruments were already listening. The Murchison Wide Field Array, comprised of hundreds of bow-tie-shaped antennas, had been probing the structure of the early universe through interferometric imaging, searching not for global signals, but for spatial fluctuations in the 21 centimeter line caused by the patchy nature of rionization. The local indigenous Wajari Yamaji people, stewards of the land, have poetically described the MWA as the ear that listens to the sky. Now, the Murchison site is preparing for the most ambitious project in the history of radio astronomy, the Square Kilometer Array. When complete, the SKA will consist of over 130,000 antennas distributed across the Australian desert. It will have the sensitivity to detect an airport radar from 10 light years away, and will be capable of mapping the epoch of rionization and the tail end of the cosmic dark ages with unprecedented resolution. And yet even the quiet Murchison region is not immune to interference. Human radio transmissions, satellite communication, and atmospheric disturbances continue to challenge ultra-sensitive observations. The ultimate destination for uncontaminated cosmology may lie beyond Earth entirely. Plans are already underway to deploy radio antennas on the far side of the Moon, a location naturally shielded from Earth's radio noise. There, in the permanent radio silence beneath the lunar regolith, astronomers hope to finally detect the primordial signal in its purest form. The pursuit is not merely technical, it is philosophical. The universe was dark for nearly 200 million years, not because nothing was happening, but because our instruments and senses were not attuned to its language. To optical eyes, the early cosmos appears blank, devoid of structure or meaning. But to a properly tuned antenna, the sky becomes alive with history. The 21 centimeter line, faint, elusive, and ancient, carries with it the tale of hydrogen clouds, cooling, collapsing, and forming the first stars. It chronicles the transition from plasma to atoms, from darkness to light, from silence to symphony. The EDGE's experiment, despite its debated result, opened a new chapter in our exploration of the universe's earliest epochs. It reminded us that even in apparent silence, the universe has a voice. And now, with every new generation of radio instrument, we are learning how to listen more carefully. The Dark Ages were never truly dark, not to the sky itself, nor to the photons that have traveled billions of years to reach us. They were simply waiting for the right kind of eye.
What if the entire universe was built from invisible bricks, smaller than anything we could ever see? What if every star, every planet, even you and I, were made from the same fundamental pieces? And what if, at the dawn of time, not a single one of them existed? The ship hums softly as it pierces the void, its frame trembling with anticipation. A crew, tense but determined, embarks on a voyage not across solar systems or galaxies, but into a realm far stranger. They are not astronauts, but atomonauts, explorers venturing into the heart of matter itself. Their mission, to traverse the inner architecture of the simplest atom in the universe, hydrogen. Departing from its solitary proton, they set out in search of the elusive electron, that dances invisibly in the space around it. Unlike the moon-bound journeys of Apollo, which spanned mere tens of Earth diameters, this expedition covers a space unimaginably vast in relative scale, more than 63,000 times the width of their homeworld. But size is not the only strangeness. This isn't an orbit as Newton imagined, nor a path we can trace with certainty. In the quantum realm, the electron does not follow a neat trajectory. It exists in a haze of probability, a shimmering cloud of possibilities. To land is impossible, to locate is uncertain, and yet everything in the known universe is built from such mysteries. These atoms, tiny, unknowable, yet persistent, are the cosmic Lego bricks from which all structure arises. Stars, oceans, minds, and memories, all woven from these quantum whispers. And yet, at the very beginning, there were none. Not one atom stirred in the newborn cosmos. So where did they come from? How did something so fundamental emerge from a universe that began with nothing? Let us begin the smallest place imaginable to answer the biggest questions we've ever asked. The first light in the universe. Where did the first light come from? And what does it reveal about the birth of atoms, the fabric of our cosmos, and the nature of existence itself? A storm churns across the Black Sea. The tranquil surface, once a polished mirror to the sky, becomes a chaos of wind and wave. In the midst of this watery turmoil drifts a fragile kayak, barely more than a silhouette against the gray tumult. Inside it are two figures, a young physicist and his new bride. They are fugitives, not from war, but from an intellectual prison, fleeing a state increasingly hostile to curiosity, reason, and the pursuit of truth. The year is 1932. The physicist is George Gamow, born in Odessa, already known among European scientists for his brilliant theoretical insights. With him is Lyubov Volkmantseva, whom he affectionately calls Ro, after the Greek letter. Their union, both romantic and intellectual, is born under duress. In the Soviet Union, the winds have turned against scientists, with foreign ties or unconventional ideas. Travel abroad is tightly controlled. Gamow, eager to present his latest research at a conference in Rome, finds himself repeatedly stalled by Soviet bureaucracy. The passport office in Leningrad offers him no escape, only delay. But in that very same office, amid endless queues and shattered hopes, he meets Ro. They fall in love. They marry. And soon after, they make a bold and desperate decision to flee across the Black Sea and seek asylum in the West. Their plan is as daring as it is unlikely. They aim to reach Turkey by sea, navigating under cover of darkness, with only an old kayak and Gamow's Danish motorcycle license, acquired during his time with Niels Bohr in Copenhagen, as their hope for a plausible identity. The goal is simple: land on a Turkish beach, claim to be Danish, and plead for help from the Danish embassy in Istanbul. At first, nature is on their side. Calm waters, light winds. But by the second morning, the sea turns savage. A violent storm rises, and their fragile vessel is no match. Exhausted, delirious, they are cast adrift and blown back toward Crimea. Their escape seems doomed, but eventually, with persistence and luck, they succeed. By 1934, they have left the Soviet Union behind for good, arriving in the United States, where Gamow would spend the rest of his life. And yet, the ideas born in his mind and the collaborations he would foster would help reshape our understanding of the entire universe. In the late 1920s, science was undergoing a revolution. Just 3 years before Gamow's escape, American astronomer Edwin Hubble had published findings that shook the foundations of astronomy. Galaxies, those distant glowing spirals, were not stationary. They were moving away from us, and not slowly. The further away they were, the faster they receded. If space itself was stretching, then it followed logically that the universe must have once been much smaller. Wind back time far enough, and every star, every planet, every atom must have been compressed into a single, unimaginably dense point. The idea would come to be known as the Big Bang, but in truth, it was not new to Gamov. Nearly a decade earlier, back in Leningrad, he had studied the equations of Alexander Friedmann, the Russian physicist who first derived a model of an expanding universe from Einstein's general relativity in 1925. The seeds of the Big Bang had been planted long before Hubble's observations. When Gamow arrived in America, his primary research interest was not cosmology, but the processes that power stars. Specifically, he was fascinated by nuclear fusion, the transformation of lighter atomic nuclei into heavier ones under immense pressure and temperature, releasing energy in the process. He understood that the same conditions that fuel the stars must once have existed throughout the entire cosmos long ago. In 1945, shortly after the end of World War II, Gamow began to connect the dots. He wrote to his old mentor, Niels Bohr, noting his growing interest in applying stellar physics to the conditions of the early universe. What if the entire cosmos, in its infancy, had once resembled the core of a star? Together with his student Ralph Alpher, Gamow developed a bold hypothesis that the early universe was hot, dense, and filled not with matter, but with radiation, specifically electromagnetic radiation. In their 1948 paper, often humorously referred to as the Alpha Beta Gamma paper, they proposed that shortly after the Big Bang, the universe was dominated not by atoms, but by light itself. This radiation, what physicists call electromagnetic energy, was not the kind of light our eyes are sensitive to. It spanned a vast spectrum, from high-frequency gamma rays to low-frequency microwaves. Just as there are sounds beyond the range of human hearing, so too there are wavelengths of light beyond our sight. But even though invisible to our eyes, this light held the power to shape matter. In the early universe, matter and light were inseparably intertwined. Photons, the particles of light, were trapped in a sea of charged particles, protons, electrons, and nuclei. The universe was opaque, like the interior of a star. Light could not travel freely. It bounced endlessly off charged particles in a chaotic dance. This era is sometimes called the photon epoch. It lasted for tens of thousands of years. During this time, matter was still forming, but radiation ruled. As the universe expanded, it cooled. Lower temperatures allowed protons and electrons to combine and form neutral hydrogen atoms, a process known as recombination. This is somewhat of a misnomer, as it was the first time these particles had ever combined in the universe. But the terminology stuck. With electrons now bound to protons, the universe became transparent for the first time. Photons were no longer scattered by free charges. They could finally move unimpeded, traveling vast distances without interruption. This release of photons, this first escape of light, is what we call the cosmic microwave background. Though we now detect it as faint microwave radiation, this light is a snapshot of the universe in its infancy, a moment frozen in time. It holds the patterns of tiny temperature fluctuations, the seeds of galaxies and cosmic structures that would form billions of years later. It is, quite literally, the first light of the cosmos. They also investigated what the early universe might have synthesized. Could all the elements we see today, carbon, oxygen, iron, have formed in that primordial fireball? Their conclusion was that only the lightest elements, hydrogen and helium, and trace amounts of lithium could have formed during the Big Bang. Heavier elements, they argued, must have been forged later, in the hearts of stars. This idea, now known as Big Bang nucleosynthesis, remains a pillar of modern cosmology. In those early dense epochs, the universe was dense enough for pressure waves, compressions, and rarefactions to ripple through it. These primordial sound waves, now stretched by billions of years of cosmic expansion, left their imprint on the large-scale structure of the universe. We call these patterns baryon acoustic oscillations. Though inaudible now, far below the threshold of human hearing, these waves can be detected through sophisticated surveys like the Sloan Digital Sky Survey. In a poetic gesture, physicist John G. Kramer even converted these ancient oscillations into audible sound using data from the early universe. The result? A deep, eerie rumble, a cosmic echo from the dawn of time. And so, from a stormy kayak voyage across the Black Sea to the luminous echoes of the Big Bang, we follow a thread of human curiosity that stretches across oceans, decades, and cosmic epochs. Gamov's life was emblematic of the power of science to transcend borders, political, geographical, and even temporal. His ideas helped illuminate the very origins of matter and light. The radiation that first poured across the newborn universe now bathes us from every direction, whispering the history of everything that has ever been. All of it, every star, every atom, every breath you take, can be traced back to those first few 100,000 years, to that light, to those waves, to the moment when the fog lifted and the universe opened its eyes. And all of it began with a question, not just where did everything come from, but how did the first light begin to shine? The weirdest object in the universe. Imagine yourself lost in a maze so dense, so impenetrable that every step forward ends in a wall. Turn left, dead end. Turn right, another. No landmarks, no pattern, no exit. Claustrophobia builds not from darkness, but from the realization that space itself offers no release. This was the condition of light in the earliest moments of the universe. In the seconds following the Big Bang, light was not the liberating, illuminating phenomenon we know. It was a prisoner of its own making, ensnared in a trap forged by its deep relationship with matter. Wherever photons tried to travel, they collided with a relentless soup of subatomic particles, bouncing, scattering, imprisoned. But to understand why light was caged, we must first understand what light is. Light, for all its elegance, is energy incarnate, a vibration in the fabric of the electromagnetic field. And energy, as Einstein taught us, is interchangeable with mass. In the high-energy furnace of the infant universe, light did what it could rarely do today. It shapeshifted into matter. Just fractions of a second after the universe was born, the searing temperatures reached over a quadrillion degrees. In these conditions, the energy of photons was so immense that light spontaneously transformed into particles, electrons, quarks, neutrinos, and their antimatter twins. Matter began to dominate the universe, but not yet in the form we recognize. At this stage, it was wild, chaotic, and unbound. To build atoms, those structured, composed units that underpin the universe, we needed more than just electrons. We needed protons, and for that, we needed something even more elementary: quarks. Quarks come in 6 varieties or flavors: up, down, charm, strange, top, and bottom. But only 2 are needed for the architecture of ordinary matter: up and down quarks. A proton is composed of 2 up quarks and 1 down quark, while a neutron is made of 1 up quark and 2 down quarks. These combinations sound simple, but the forces binding them are anything but. Quarks possess electric charge. Up quarks are positively charged, and down quarks are negatively charged. So how did 2 positive charges sit together within a proton without flying apart? The answer lies in one of the 4 fundamental forces of nature, the strong nuclear force. While gravity governs planets and stars, and electromagnetism dictates the behavior of light and charge. The strong nuclear force is the mighty glue that holds the nucleus of every atom together. It is, by every measure, the most powerful force known, 10 to the power of 38 times stronger than gravity. Yet this immense power comes with a caveat. It acts over vanishingly small distances, less than a trillionth of a millimeter. In the scorching, turbulent early universe, where particles zipped around with almost unimaginable kinetic energy, even this strong force was overwhelmed. Quarks could not bind into stable triplets like protons and neutrons. Not yet. Only when the universe had expanded and cooled for a millionth of a second did temperatures fall to about 1 trillion degrees. Then, and only then, could quarks be tamed into nucleons. The first protons and neutrons formed, stable, robust, and ready for the next stage in matter's long journey toward atoms. And yet, the story of the proton, far from being one of simplicity, is among the strangest in physics. Ask a physicist where a proton is, and they may smile ruefully. It's complicated, they'll say, because despite decades of investigation, the proton remains one of the most bizarre, elusive, and intricate objects in the universe. For one thing, the 3 valence quarks that compose the proton account for only 1% of its mass. The other 99% comes not from stuff in the traditional sense, but from a swirling storm of virtual particles and force carriers. Chief among them, the gluon. Gluons are the messengers of the strong nuclear force. They dart between quarks, binding them through a dance of continuous exchange. But unlike the photon, which carries the electromagnetic force without interacting with other photons, gluons interact with each other. This creates a tangled web of field interactions, spawning a sea of virtual particles. These sea quarks and their antiparticles briefly blink into existence within the proton. They borrow energy from the vacuum, just enough, just briefly enough, to satisfy quantum uncertainty. They annihilate and reform in a frenetic blur. The result is a particle that is more cloud than core, a restless, stormy sea of fluctuating mass and energy. In truth, the proton is less an object than a process, a bubbling, dynamic storm of quantum activity. Experiments like those at the relativistic Heavy Ion Collider, RHIC in New York, have confirmed that the proton's mass is emergent. It arises not from the mass of its constituents, but from the energy of their interactions. Even stranger, these virtual sea quarks can include heavier varieties, like charm quarks, that are far more massive than the proton itself. A single charm quark has about 1.5 times the mass of the entire proton, yet they appear, briefly, without breaking the laws of conservation. This quantum weirdness, particles popping in and out of existence like flickering ghosts, doesn't just influence the proton, it defines it. Now that protons and neutrons exist, the universe's expansion continues. Particles slow, space cools, and a crucial window opens. Roughly 1 second after the Big Bang, the cosmos reaches a temperature of around 10 billion degrees. This is cool enough for protons and neutrons to begin binding together, held by the strong force, into simple nuclei. The first of these is the deuteron, composed of 1 proton and 1 neutron. It is the precursor to all heavier atomic nuclei. Enter George Gamow and his collaborator Ralph Alpher. In 1948, they published a groundbreaking paper, brief but revolutionary, in which they outlined the series of nuclear reactions that transformed the early universe's hydrogen into helium. This process, called Big Bang nucleosynthesis, took place within a 20-minute window. During this time, the conditions were just right for nuclear fusion to operate across the entire cosmos, just as it would billions of years later in the cores of stars. Through a rapid series of reactions, deuterons fused with additional protons and neutrons, creating helium-3, helium-4, and a trace of lithium. By the end of this short epoch, About 25% of the universe's mass was in helium nuclei. The remaining majority was hydrogen. But this was not yet the formation of atoms. What was created in the first 20 minutes were nuclei, the dense, positively charged cores of atoms. To complete the picture, they needed electrons. Electrons, lighter and more elusive than protons, had been present since the very beginning. But they roamed freely, constantly interacting with photons and other charged particles. Their journey into bound orbits required a universe that had cooled significantly more. The electromagnetic force, the one responsible for attracting negatively charged electrons to positively charged nuclei, is much weaker than the strong force. To give it a chance to bind electrons into orbits, the universe needed to cool to just 4,000 degrees Kelvin. That would take time. It was only then, in this cooler and more expanded cosmos, that electrons could finally settle into orbitals around nuclei, forming neutral atoms. This moment is called recombination, though in truth it was the first combination. With electrons now bound, photons were freed from constant scattering. Light, for the first time, could travel unimpeded. This release of photons is what we now observe as the cosmic microwave background, the afterglow of the Big Bang, stretched into microwaves by billions of years of cosmic expansion. It is the oldest light in the universe, a relic from a time when the first atoms were born. But even these electrons, the humble negative companions to protons, harbor strangeness. Electrons, as far as we can tell, are point particles. They have no internal structure, no spatial extent. They are, in the language of physics, truly fundamental, and yet they defy simple description. Electrons do not orbit nuclei in neat planetary tracks. Quantum mechanics tells us that such imagery is misleading. Instead, electrons exist as probability clouds, their positions uncertain, their velocities unknowable with precision. The Heisenberg uncertainty principle ensures that the best we can do is calculate the likelihood of finding an electron in a certain region. Moreover, electrons possess spin, a quantum property that defies classical analogy. Though we often describe it as rotation, this is a metaphor. Electrons do not spin in space. Yet their spin governs magnetic interactions and determines how electrons fill atomic orbitals, giving rise to the periodic table and the structure of matter. Spin half particles like electrons also exhibit another counterintuitive behavior. They must rotate 720 degrees, not 360, to return to their original quantum state. This bizarre fact lies at the heart of quantum field theory and hints at the deep symmetries that underlie our universe. Thus, within every atom, within every breath of air, every drop of water, every star and cell and stone, is a swirling, probabilistic hall of mirrors, quarks that blink in and out of existence, gluons that bind the impossible, electrons that refuse to be pinned down. What seems so tangible and solid is built atop a bedrock of uncertainty and abstraction. And yet from this chaos, order emerges. Atoms became the building blocks of molecules, molecules the scaffolding for chemistry, chemistry the stage for biology. The structure of the universe, galaxies, stars, planets, people, flows from the first moment when light was set free by the formation of neutral atoms. In 1948, Ralph Alpher and Robert Herman predicted that the glow from that moment of release, the relic radiation of recombination, should still be visible. It would have cooled by now, they reasoned, stretched into microwaves. But their insight, profound as it was, went largely unnoticed for decades, until two radio astronomers working on a different problem in Holmdel, New Jersey, stumbled across a hiss that came from every corner of the sky. They had found the ghost of recombination, the first light, the proof that the universe began hot, dense, and full of potential. That light is still with us, whispering across the eons. It is the silent testimony of a time when the weirdest object in the universe, the atom, was first forged, from light and fire. Seeing the Big Bang, a tale of invention, serendipity, and the echoes of creation. On a crisp September morning in 1941, a young Robert Dix stood atop the radiation laboratory at the Massachusetts Institute of Technology, cradling a device of his own design. At just 25 years old, fresh from completing his PhD, Dick was already making waves. Yet few could foresee how his curiosity, first sparked by war, then stoked by wonder, would help reveal the earliest light in the universe. Dick's arrival at MIT coincided with one of the most pivotal moments in modern history. The world was already 2 years into the Second World War, and while the United States had not yet joined the fight, preparations were underway. Within weeks of his arrival, Japan bombed Pearl Harbor, and the U.S. entered the conflict the very next day. This marked the beginning of Dick's career in wartime science, a crucible of innovation that would leave lasting imprints on both technology and cosmology. At MIT, Dick's task was urgent and critical: radar development. The term radar had only recently been coined by the U.S. Navy. The principle was simple yet powerful: emit bursts of radio waves and detect their echoes off distant objects, such as enemy aircraft. However, early radar systems were crude. Their long radio wavelengths meant the details they captured were limited, much like trying to perceive fine brushstrokes through frosted glass. Dick, with his keen engineering instincts and flair for invention, turned his attention to microwaves. Unlike radio waves, microwaves have much shorter wavelengths. The advantage was clear: finer resolution and greater sensitivity. This led to one of Dick's key wartime inventions, the Dick radiometer, a device finely tuned to detect faint microwave signals with unprecedented precision. Yet for all his contributions to military technology, Dick's mind often wandered skyward, beyond the threats of bombers and missiles. He began to wonder, were there signals, not of war, but of nature, coming from space? Were there whispers of ancient cosmic events hidden in the microwave part of the electromagnetic spectrum? This thought stayed with him, quietly simmering for over a decade. After the war, Dick returned to academia, joining the faculty at Princeton University. There, he rekindled his interest in the cosmos and began to seriously consider one of the most profound questions in all of science. How did the universe begin? At the time, the Big Bang theory was gaining traction, but it was far from universally accepted. The idea that the universe originated from an unimaginably hot, dense state and had been expanding ever since was as philosophically jarring as it was scientifically compelling. How does something come from nothing? Was and remains a natural reaction to the theory. Dick, never satisfied with easy answers, explored alternatives. He considered a cyclical universe, one that expands, slows, reverses, and collapses in a grand Big Crunch, only to explode once more in a renewed Big Bang. An eternal cosmic heartbeat. Within this framework, Dick envisioned a dramatic phase in the universe's history. As the cosmos contracted, temperatures would skyrocket, reducing matter to a primordial soup of protons, electrons, and subatomic debris. This incandescence, a searing fireball of radiation and particles, would be the crucible from which the universe would be reborn. During the subsequent expansion, the fireball would cool, and conditions would again become favorable for atoms to form. This process, he reasoned, could leave behind a telltale sign: residual radiation from that fiery epoch, lingering like a ghost in the cosmos. Unbeknownst to Dick at first, this idea was not entirely novel. As early as 1948, physicist George Gamow and his collaborators Ralph Alpher and Robert Herman had predicted just such a relic. They hypothesized that if the early universe had been hot and dense, it would have emitted thermal radiation, initially visible light, that would persist even today, albeit stretched by cosmic expansion into the microwave part of the spectrum. Dickey independently arrived at the same conclusion. Building on his deep knowledge of microwave detection, he proposed searching for this fireball radiation, a fossil echo of the universe's formative moments. He surmised that over the billions of years since its emission, this radiation would have been redshifted by the expansion of space, moving it from the visible into the microwave region. If it existed, it should still be detectable using the kind of instrumentation he had been refining for decades. He began preparing for the observation campaign in the early 1960s, assembling a team and designing equipment. But fate intervened. Just 45 miles away, in Holmdel, New Jersey, two radio astronomers, Arno Penzias and Robert Wilson, were working on a very different problem. They weren't hunting cosmic relics. Instead, they were trying to eliminate noise from their measurements of satellite signals, using the massive 6-meter Holmdel horn antenna at Bell Labs. The noise they encountered was persistent and puzzling, a steady isotropic hiss that refused to go away. They were meticulous in their troubleshooting. Local sources of interference were ruled out. They cooled their receiver to near absolute zero using liquid helium, eliminating thermal noise. Still, the signal remained. Eventually, they discovered a pair of pigeons had taken up residence in the antenna, leaving behind what they later described as white dielectric material. The pigeons were gently removed and relocated, only to return. Eventually, with regret, they were euthanized. The antenna was cleaned, but the hiss endured. The signal, it seemed, was coming from every direction in the sky. Confounded, Penzias reached out to colleagues for insight. One of those calls went to Robert Dicke. At that very moment, Dicke and his team were in the middle of planning their own search for the fireball radiation. When he heard what Penzias described, Dicke turned to his colleagues and said, simply, "Well, boys, we've been scooped." Penzias and Wilson had unwittingly detected the cosmic microwave background, the faint afterglow of the Big Bang, the exact signature Dick had set out to find. Their serendipitous discovery, published alongside a companion theoretical paper from Dick's group, confirmed one of the most profound predictions of modern cosmology. In 1978, Penzias and Wilson received the Nobel Prize in Physics. Dick, Gamow, Alpher, and Herman would never claim that honor. Yet their contributions laid the foundation for what is now one of the cornerstones of cosmological science. The CMB is more than just a technical curiosity. It is a snapshot of the universe when it was just 380,000 years old, a newborn in cosmic terms. At that time, the universe had cooled enough for electrons and protons to combine into neutral hydrogen atoms, allowing light to travel freely for the first time. That light, now stretched into microwaves, fills the universe. If the universe were a 40-year-old human, the CMB is the equivalent of a photo taken in the first 10 hours of life, a baby picture of everything. Yet this image is not smooth. Embedded in the CMB are minute temperature fluctuations, tiny differences in density, that seeded the large-scale structure of the cosmos. Where there was slightly more matter, gravity pulled in more, amplifying the contrast. Over time, these regions became the galaxies, clusters, and filaments we observe today. These fluctuations also preserve the echoes of sound waves, pressure oscillations in the hot plasma of the early universe, known as baryon acoustic oscillations. Like ripples frozen in time, they mark the rhythmic pulse of the infant cosmos. Today, surveys such as the Dark Energy Survey in the Chilean Andes map the universe in stunning detail. They reveal a vast, web-like structure, superclusters of galaxies and immense voids, all tracing the patterns etched into the CMB nearly 14 billion years ago. The seeds of the present were sown in the earliest moments, and remarkably, you don't need a giant telescope to sense this ancient light. In the era before digital broadcasting, an old analog television set could detect it, tune between channels, and a portion of the static, the snow dancing across the screen, was the cosmic microwave background, whispering across time. This signal will outlast us. It will fade only after trillions of years of continued expansion, eventually stretched beyond detection. But for now, it remains a testament to a moment when atoms first formed, when the universe became transparent, and when the light of creation began its journey to us. It's tempting to think that atoms were an inevitable outcome, that in any universe filled with light and matter, they would naturally form. But this is far from certain. The conditions had to be just right. A slightly different rate of expansion, a different balance of forces, and atoms might never have formed. No stars, no galaxies, no life. The formation of the first atom wasn't a guarantee. It was a cosmic triumph, and the light from that triumph still surrounds us. Woven into the very fabric of space, it is the echo of a fireball that once lit up the universe and has never truly gone dark. Why atoms? Imagine, for a moment, standing blindfolded before 24 loaded rifles, their barrels aimed squarely at your chest. You hear the subtle metallic clicks as the triggers are drawn back. Feel the tension of your final breath and brace for oblivion. Then, miraculously, every single shot misses. Not one, not two, but all 24 projectiles fail to find their mark. You survive. This dramatic thought experiment, proposed by Canadian philosopher John Leslie in his 1989 book, Universes, serves as a powerful metaphor for the seemingly improbable circumstances that allow our universe to exist, and more specifically, to allow atoms to exist at all. Just as it only takes one bullet to end a life, it would take only a minuscule tweak in the laws of physics to snuff out the existence of atoms. Yet here we are, awash in a cosmos teeming with them. From the moment of its birth, 13.8 billion years ago, the universe has undergone an extraordinary transformation. It began as an almost unfathomably hot, dense, and chaotic state, devoid of any structure. Today, it contains more atoms than we could hope to count in trillions upon trillions of lifetimes. Atoms form the scaffolding of all matter, from the most distant galaxies to the neurons in your brain. We take them for granted, but their very existence is predicated upon a precise balance of cosmic parameters, each one tuned so delicately that even the slightest adjustment would obliterate this fragile architecture. Let us consider a metaphorical control panel covered with dials, sliders, and switches, each governing a fundamental property of the universe: the masses of subatomic particles, the strength of fundamental forces, the rate of cosmic expansion. Tinker even slightly with the settings on this cosmic console, and atoms, the bedrock of chemistry and biology, would unravel. One of the most crucial parameters is the ratio between the size of electron orbits and the size of the atomic nucleus. For an atom to be stable, electrons must orbit at distances far greater than the size of the nucleus. If the electromagnetic force were even slightly stronger, electrons would spiral inward, crashing into the nucleus like satellites burning up on atmospheric re-entry. If the force were weaker, electrons would escape altogether, leaving protons isolated and chemistry impossible. But it's not just electromagnetism. The strong nuclear force, which binds protons and neutrons within the nucleus, must also be precisely tuned. Weaken it by just a small fraction, about 9%, and it would be too feeble to hold protons and neutrons together in the simplest nucleus, the deuteron. No deuterons, no fusion in the early universe. Strengthen it by just 2%, and 2 protons could bind into a diproton, a particle never observed in nature. Such particles would have rapidly fused into helium during the Big Bang, depleting the universe's supply of hydrogen, the foundational element upon which stars and life depend. The degree of fine-tuning required is staggering. A physicist would say these forces are finely tuned, a term that belies the almost cosmic improbability of the settings being just right. This idea, now central to debates in cosmology and philosophy, was first articulated in a meaningful way by physicist Robert Dicke in 1961. He argued that the universe appears biophilic. Its parameters fall into a narrow range that permits life. But it isn't only the fundamental forces that are delicately arranged. Consider the masses of the particles themselves. The neutron is just slightly heavier than the proton, by about 1/7 of 1%. This small disparity is critical. Were the neutron lighter, it wouldn't decay, and the balance of matter in the universe would be entirely different. If it were much heavier, it wouldn't form stable nuclei at all. If the electron were heavier than the mass difference between proton and neutron, it could be captured by protons, transforming them into neutrons and disrupting atomic structure altogether. These masses depend in turn on the quarks that make up protons and neutrons. A proton is composed of 2 up quarks and 1 down quark, while a neutron contains 2 downs and 1 up. The down quark is slightly more massive than the up quark, a difference that tips the scales just enough to make the neutron heavier. Were this mass difference altered even slightly, the entire narrative of the universe would change. Neutrons could decay into protons in an uncontrolled manner. Deuterons would become unstable, and the formation of elements beyond hydrogen would be thwarted. No oxygen, no carbon, no periodic table. And yet, through a delicate interweaving of forces and particles, atoms came into being. Their progenitors, the quarks, gluons, electrons, emerged within microseconds of the Big Bang. Within minutes, protons and neutrons fused into simple nuclei. Hundreds of thousands of years later, these nuclei captured electrons to form neutral atoms. Stars lit up, forged heavier elements, and exploded them into space, seeding the cosmos with the raw ingredients for planets, oceans, and life. Such a tale naturally invites questions. Why is the universe so precisely arranged? Why does it permit atoms at all? Why do we find ourselves in a cosmos capable of not only building complex structures, but also of reflecting on its own origins? To explain this fine-tuning, scientists and philosophers have proposed 3 broad possibilities. The first is sheer chance. Perhaps we simply won the cosmic lottery. The parameters had to take some values, and by astronomical coincidence, they fell into the narrow range that permits atoms. This explanation is logically consistent, but emotionally unsatisfying to many. The odds of getting all the settings right are comparable to selecting a single star, the Sun, out of a bag containing every star in the observable universe. Possible? Yes. Likely? Hardly. The second possibility posits design. Perhaps some conscious agent, be it a deity or an advanced civilization, deliberately tuned the settings. The universe, in this view, is a kind of simulation, a grand design meant to host life. While this idea has intuitive appeal, especially in the wake of our own increasing prowess with simulations and artificial intelligence, it steps beyond the empirical into the metaphysical. The third explanation, and perhaps the most scientifically adventurous, is the multiverse. In this framework, our universe is but one of countless others, each with its own set of physical laws. These alternate universes could arise from different quantum fluctuations in a grand cosmic landscape, as suggested by theories like eternal inflation or string theory. In this view, all possible values of the dials are realized somewhere. Most of these universes are sterile. No atoms, no stars, no life. but a few, like ours, happen to have the right settings. And naturally, we find ourselves in one of those rare few where atoms exist, because only such a universe can produce observers to contemplate it. This line of reasoning is a form of the anthropic principle. It doesn't explain why the universe is finely tuned. It merely reframes the question. Out of all the possible cosmic realities, we could only ever exist in one that permits our existence. The idea of the multiverse remains speculative, but it's not without support. Observations of the cosmic microwave background, the afterglow of the Big Bang, suggest that inflation, a rapid expansion of the early universe, did occur. And in many versions of inflation, it never ends completely, giving rise to a branching tree of universes, each with different properties. Regardless of which explanation is correct, chance, design, or multiverse, the conclusion remains the same. The existence of atoms is astonishingly contingent. The conditions required for them to exist are so precise, so interdependent, that their presence in our universe is nothing short of a cosmic miracle. And what a journey those atoms have taken. Forged in the hearts of stars, they've been scattered across galaxies, gathered into planets, dissolved in oceans, and eventually woven into the complex biochemistry of life. Some of them now sit inside the neural circuits of your brain, enabling you to read and ponder these words. The atom, that most elementary unit of matter, is the cornerstone of a vast and intricate story. A story of precarious balances, improbable coincidences, and profound implications. It is the narrative thread that runs through physics, chemistry, biology, and consciousness itself. As we gaze deeper into the cosmos, as we delve further into the quantum realm, we are reminded again and again of how rare and precious our existence truly is. And perhaps, in the end, it is this very improbability that makes the story of atoms and the story of us so endlessly compelling.
What would it be like to fall into a black hole? Would you be able to perceive its boundaries, or would reality itself begin to dissolve around you? And what role do these cosmic behemoths play in shaping the very fabric of the universe? To answer these questions, we must journey to one of the most enigmatic and extreme regions of space, the heart of our own galaxy, where an immense and invisible force dominates its surroundings. At first glance, the region appears deceptively bright. Unlike the vast emptiness of interstellar space, the galactic core is a crowded and chaotic place. A dense concentration of stars, millions of them, whirl in complex orbits, their trajectories tracing an invisible gravitational master. At the very center of this celestial ballet lies Sagittarius A*, a supermassive black hole with a mass roughly 4 million times that of the Sun. Unlike an ordinary star, Sagittarius A* is not a visible sphere of light but an absence, a void so absolute that even light itself cannot escape its grasp. However, its presence is betrayed by the chaotic motions of the stars that encircle it and by the glowing ring of superheated matter spiraling into its depths. This luminous accretion disk, composed of gas and dust stripped from unfortunate celestial bodies, radiates intensely as gravitational forces compress and heat it, unleashing powerful X-rays and gamma rays into space. As you approach this region, the first subtle effect you notice is an inexorable tug, a gravitational pull that intensifies as you drift closer. Soon, you find yourself drawn into an orbit around the black hole, carried along by the spiraling currents of the accretion disk. Here, amidst the swirling chaos, space itself is warped. The immense gravitational forces stretch and distort the very fabric of space-time, creating the illusion that distant starlight bends and loops around an unseen center. Your body is subjected to extreme conditions. Friction from high-energy particles batters you with radiation, shredding your DNA beyond repair. But these physical afflictions pale in comparison to the effects of gravity itself. The closer you move to the black hole's event horizon, the boundary beyond which escape is impossible, the more time itself begins to behave strangely. To an external observer, your descent appears to slow, as if you are falling ever more sluggishly toward the edge. In their frame of reference, you never quite cross the horizon. Instead, you seem to linger indefinitely, your image growing redder and dimmer as gravitational time dilation stretches your wavelengths into oblivion. But from your own perspective, nothing unusual occurs until you finally pass the event horizon and any remaining connection to the universe is severed. Beyond this point, conventional physics ceases to offer a clear explanation. Space and time swap roles. Rather than moving through space toward the singularity, it is now time itself that pulls you inexorably inward. No force, no intervention, nothing in the known universe can halt your fall. What awaits at the center remains an unsolved question. General relativity predicts an infinitely dense singularity, a point where gravity becomes infinite and our understanding of physics breaks down. Quantum mechanics, however, suggests that some yet undiscovered mechanism may prevent such an extreme fate. The existence of black holes, first postulated in 1783, has transformed our understanding of the cosmos. No longer mere theoretical oddities, they are now recognized as fundamental components of the universe. Supermassive black holes like Sagittarius A** are believed to reside at the heart of nearly every galaxy, playing a crucial role in their evolution. The energy released by their accretion disks can trigger star formation or, conversely, suppress it, regulating the growth of galaxies over cosmic timescales. Yet, one of the greatest mysteries remains. How did these supermassive black holes form in the first place? Did they grow from the collapse of the first massive stars, gradually accumulating matter over billions of years? Or were they seeded by exotic processes in the early universe, forming almost simultaneously with the first galaxies? As astronomers peer deeper into the cosmos, they search for answers, hoping to uncover the origins of these enigmatic giants and, in doing so, illuminate the story of the universe itself. The first black hole. Rain lashes against the tin roof of the makeshift shelter, cascading in rivulets down its sides and pooling into the muddy trenches below. A biting December wind weaves through the desolate encampment, its chill gnawing at the weary soldiers huddled beneath the slate-gray sky. The distant echoes of gunfire and artillery have, for now, fallen silent. Inside the dimly lit refuge, a senior lieutenant shifts his focus from the grim realities of war to the stack of dispatches on his desk. The year is 1915. The place, the Eastern Front of World War I. The lieutenant is Karl Schwarzschild. A distinguished physicist and director of the Astronomical Observatory in Potsdam, Schwarzschild was drawn into the war effort, applying his formidable mathematical prowess to the calculations of ballistic trajectories. Yet, tonight, amid the chaos and destruction, something unexpected captures his attention. Among the dispatches, a thick envelope bears the unmistakable handwriting of his colleague and friend, Albert Einstein. Inside lies a paper titled The Field Equations of Gravitation, a work destined to redefine our understanding of the universe. In it, Einstein presents the mathematical scaffolding of what would later be known as general relativity, a theory that describes how mass distorts space-time and how that curvature, in turn, dictates the motion of matter. The equations are intricate, their reasoning recursive, their solutions elusive. Yet, by the flickering light of a lamp, Schwarzschild pores over them with fervor, his mind alight with curiosity. Despite the war raging around him, within days Schwarzschild composes a letter back to Einstein. It contains something extraordinary, a precise and elegant solution to the equations, a discovery that would have profound implications for the nature of gravity and the cosmos itself. In his letter, he writes with characteristic humility, "As you see, the war treated me kindly enough, in spite of the heavy gunfire, to allow me to get away from it all and take this walk in the land of your ideas." Schwarzschild's solution describes the curvature of space-time surrounding a perfectly spherical mass. But embedded within it is a prediction that stretches the limits of comprehension. If an object were compressed beyond a critical threshold, later termed the Schwarzschild radius. Its gravitational pull would become so immense that nothing, not even light, could escape its grasp. This was, in essence, the theoretical blueprint for what we now call a black hole. The Schwarzschild radius is determined by three fundamental quantities: the universal gravitational constant, the speed of light, and the mass of the object in question. Since the constants remain fixed, the radius depends solely on mass. More mass means a larger Schwarzschild radius. For a human, this critical size would be roughly a millionth the diameter of a single cork, an unfathomably tiny scale. For Earth, it measures just 9 millimeters. For the Sun, approximately 3 kilometers. However, since real-world celestial bodies exist far beyond these minuscule thresholds, their gravity remains within normal bounds. Only under extreme conditions, where matter is compacted into an inconceivably small volume, would Schwarzschild's prediction take tangible form. Though Schwarzschild's intellect endured the horrors of war, his body did not. He succumbed to a debilitating illness before he could witness the full ramifications of his discovery. For years, the idea of such an object, one where space-time curvature became infinite, was dismissed as an abstract mathematical curiosity. Many physicists resisted the notion that such an entity could exist in nature. That skepticism began to wane in 1964. High above Earth's atmosphere, where the protective veil of air no longer blocks high-energy radiation, 2 Geiger counters aboard a rocket flight detected an enigmatic source of intense X-rays in the constellation Cygnus. The object, later named Cygnus X, 1, presented a riddle, a powerful emitter of X-rays, yet invisible to optical telescopes. Further investigation revealed startling properties. The rapid fluctuation of its X-ray emissions on timescales shorter than a second implied a compact size. But orbital measurements of a visible companion star revealed the invisible source's mass, at least 15 times that of the Sun. Such an object was too massive to be a white dwarf or neutron star. The only plausible explanation was the very entity Schwarzschild had envisioned decades earlier, a black hole. As evidence for Cygnus X, one accumulated throughout the 1970s, the scientific community finally embraced the reality of black holes. The term itself had only recently been popularized. In a 1967 NASA lecture, the physicist John Wheeler sought a more palatable alternative to the cumbersome phrase, gravitationally completely collapsed object. An exasperated audience member proposed a more succinct term, black hole. Wheeler seized upon the name, and it swiftly entered both scientific and popular lexicon. Today, we understand well how black holes like Cygnus X, one form. Massive stars, sustained by nuclear fusion, eventually exhaust their fuel. Without the outward pressure of fusion to counteract gravity, the core collapses, often triggering a supernova explosion. If the remnant core exceeds roughly 3 solar masses, no known force can resist its collapse, and a black hole is born. Encased within its event horizon, the Schwarzschild radius, lies a region from which no information can escape. The more mass it accrues, the larger it grows, devouring anything that crosses its threshold. Yet, the interior of a black hole remains a mystery. Einstein's equations suggest that at its core lies a singularity, a point where space-time curvature becomes infinite and conventional physics ceases to function. Some have speculated that these singularities might bridge to other universes, a conjecture veiled in mathematical possibility, but devoid of experimental validation. No signal, no probe, no particle can return from beyond the event horizon to offer insight into what lies within. Despite this veil of secrecy, astronomers estimate that our Milky Way harbors millions of black holes, though their small size makes them elusive. To date, only a fraction have been definitively identified. Yet, these stellar black holes are merely the lesser siblings of a far grander and more enigmatic phenomenon, the supermassive black holes that reside at the heart of every galaxy, including our own. These cosmic leviathans, millions or even billions of times the mass of the Sun, exert an influence on the evolution of galaxies themselves. Schwarzschild's wartime calculations, scribbled in the midst of battle, unlocked a gateway to one of nature's most astonishing secrets. His vision, once an obscure mathematical prediction, has since become one of the most captivating and well-substantiated pillars of modern astrophysics. And yet, even a century later, the depths of the black hole remain as unknowable as the darkness from which it draws its name. Supermassive. On April 10th, 2019, an image spread across the world at an unprecedented speed, capturing the imagination of both the scientific community and the general public. It was not a conventional work of visual grandeur, nor an intricate mosaic of detail. Rather, it was a blurred, indistinct torus of glowing orange against the vastness of an inky black void. Yet, despite its simplicity, this image was nothing short of revolutionary. It was the first direct image of a black hole, an object long theorized but never before glimpsed beyond the realm of mathematical abstraction. For centuries, black holes had remained elusive, their existence inferred only through indirect observations. Their very name is indicative of their nature. They are black by definition, absorbing all light and offering no direct visibility. Capturing an image of such an entity seemed, at first glance, to be an exercise in futility. Yet, scientists, armed with an understanding of the extreme gravitational effects black holes exert on their surroundings, devised a novel approach. A sufficiently massive black hole, enshrouded by a disk of superheated gas and dust, should radiate intensely in the radio spectrum. Given the right conditions, and with a telescope of sufficient size, this radiation could be detected. However, the black holes capable of generating such a detectable signal would have to be immense, far larger than stellar remnants. These objects, known as supermassive black holes, contain millions to billions of times the mass of our Sun and are thought to reside at the centers of nearly all large galaxies. Not only do they dominate the gravitational landscape of their host galaxies, but they may also play a critical role in their formation and evolution. Paradoxically, even as they devour surrounding material, these behemoths can influence star formation through their outflows, dispersing energy and matter across interstellar space. The fundamental nature of this relationship has led to one of the most perplexing questions in modern astrophysics. Did galaxies create their supermassive black holes, or did supermassive black holes, in some primordial form, seed the first galaxies? To uncover the secrets of these celestial giants, scientists turned first to the heart of our own Milky Way. Here, at a distance of approximately 25,000 light-years from Earth, lurks Sagittarius A*, a supermassive black hole with a mass of roughly 4 million suns. Its proximity made it an attractive observational target, but it came with unique challenges. Nestled deep within the dense core of our galaxy, Sagittarius A* is obscured by countless stars, cosmic dust, and interstellar gas. Furthermore, its relative motion across the sky due to the Earth's rotation posed additional difficulties in obtaining a long enough exposure for a detailed image. Instead, researchers focused their initial efforts on a more distant, yet more accommodating candidate, the supermassive black hole at the heart of the galaxy Messier 87. Situated 55 million light-years away in the Virgo cluster, M87's black hole dwarfs Sagittarius A*, containing an astonishing 6.5 billion solar masses. Despite its immense distance, its sheer size and the relative stability of its position in the sky made it an ideal subject for observation. The fundamental problem of imaging a black hole lies in resolution. In radio astronomy, the ability to resolve fine details is dictated by the size of the telescope aperture. To observe an object as distant and small as M87's event horizon, a telescope would need to be approximately the size of Earth itself, an apparent impossibility. The solution was both elegant and ambitious. Rather than constructing a single enormous telescope, scientists linked together an array of radio observatories scattered across the globe. This network, known as the Event Horizon Telescope, spanned from the South Pole to Spain, creating a virtual telescope with an effective aperture nearly as large as Earth. By precisely synchronizing observations from these facilities using atomic clocks, the YHT was able to collect vast amounts of data over 4 days in April 2017. Given the immense volume of information recorded, conventional data transfer methods proved inadequate. Instead, the data was stored on physical hard drives and transported to central processing centers, where teams of scientists meticulously reconstructed the image using advanced computational algorithms. After 2 years of rigorous data analysis, the result was unveiled: the first ever image of a black hole's event horizon, silhouetted against the glowing emissions of its surrounding accretion disk. The discoveries did not end with M87. In May 2022, after another 3 years of data processing, astronomers achieved a second milestone: the first image of Sagittarius A star. Despite its smaller mass compared to M87's black hole, its close proximity allowed for unprecedented insight into the structure of our own galaxy's central behemoth. This marked yet another step toward understanding the enigmatic nature of supermassive black holes. Despite these groundbreaking achievements, the question of supermassive black hole formation remains largely unresolved. How does an object grow to billions of solar masses? Some hypotheses suggest that these behemoths began as stellar mass black holes, gradually accumulating mass over billions of years through accretion and mergers. However, this explanation struggles to account for the existence of quasars, supermassive black holes observed less than 1 billion years after the Big Bang. Given the constraints of star formation in the early universe, these objects appear inexplicably massive far too soon. One proposed alternative is the existence of direct collapse black holes. Rather than forming from the remnants of dying stars, these black holes would emerge directly from the collapse of vast clouds of primordial gas. This mechanism circumvents the time constraints of gradual accretion but remains largely theoretical, as the specific conditions required for such a process to occur remain uncertain. Even more enigmatic are the so-called ultramassive black holes, such as TUN 618, which tips the scales at an astonishing 66 billion solar masses. Such giants challenge even the most generous growth models. Given that they shine as quasars, among the brightest objects in the universe, it is clear that they continue to accrete vast amounts of matter, shaping the very galaxies in which they reside. Yet, their sheer scale defies easy explanation. The final puzzle piece. As astronomers continue to refine their observations and models, one overarching mystery remains: the existence of massive black holes in the infant universe. Their presence so soon after the Big Bang suggests that our understanding of cosmic evolution is incomplete. If black holes truly require the deaths of massive stars to form, then a paradox emerges. There simply wasn't enough time for such stars to live and die in sufficient numbers. This enigma suggests that something fundamental is missing from our models. Was there an unknown mechanism that accelerated black hole formation in the early universe? Did exotic physics play a role? Or was there an undiscovered process that allowed black holes to bypass traditional growth pathways altogether? Somewhere in the depths of the cosmos, buried in the light of ancient quasars, the answers await. Whether through new observations, theoretical breakthroughs, or the next generation of telescopes, we stand on the precipice of unraveling the final secrets of these supermassive titans. What force sculpted these behemoths before the first stars were born? That, perhaps, is the next great question of modern astrophysics. Before atoms. In 1962, a 20-year-old undergraduate at Oxford University suffered what seemed at first to be an innocuous accident. He fell down a flight of stairs. His doctors dismissed it with casual advice: lay off the beer. But when his clumsiness persisted into the following year, his family grew increasingly concerned, and the young scholar was admitted to the hospital for an exhaustive series of medical tests. After 2 weeks of rigorous examinations, the physicians remained vague. They offered no definitive diagnosis, only a grim prognosis. His condition was atypical, it was expected to worsen, and they harbored little hope. The student himself did not press them for details. He simply took the vitamins they prescribed, though he could see in their eyes that they did not expect them to help. That student was Stephen Hawking. The diagnosis he had avoided confronting was a myotrophic lateral sclerosis, a neurodegenerative disease that progressively destroys motor neurons, leading to paralysis and, eventually, the loss of the ability to speak, swallow, and breathe. Doctors predicted that he had no more than 2 years to live. Hawking, however, defied those expectations. Rather than fading away, he continued his studies, taking his prescribed vitamins and persevering for 55 more years. Over the next half-century, he not only completed his postgraduate work, but became one of the most celebrated scientists of all time. His groundbreaking contributions to cosmology placed him among the ranks of Charles Darwin and Albert Einstein, and he became one of the youngest scholars ever elected a Fellow of the Royal Society. Yet, to much of the public, he remained as famous for his triumph over ALS as for his scientific achievements. But it was his science that earned him his place in history. Over the course of his career, Hawking fundamentally reshaped our understanding of black holes, the early universe, and the fundamental laws of physics. His work illuminated both the vast and the infinitesimal, and in doing so, he tackled one of the most profound questions in cosmology: what happened before atoms existed? Hawking's doctoral thesis, completed in 1966 in the shadow of his recent diagnosis, explored the great debate of the time: the origin of the universe. Inspired by the theoretical physics of black holes, he proposed that a similar mathematical singularity could describe the beginning of the cosmos itself. If black holes were born from the gravitational collapse of massive objects into an infinitely dense point, could the universe itself have emerged from such a state? Throughout the 1970s, Hawking made critical advances in our understanding of black holes. He formulated the area theorem, demonstrating that the event horizon of a black hole could never shrink. Later, in an effort to reconcile general relativity with quantum mechanics, he proposed that black holes might not be entirely black after all. Instead, he suggested they emit radiation, now known as Hawking radiation, allowing them to lose mass and eventually evaporate. Though this idea remains unconfirmed by direct observation, its theoretical implications have transformed our understanding of gravity, thermodynamics, and quantum mechanics. Yet, even as he explored the mysteries of black holes, Hawking remained captivated by the early universe. His investigations into singularities naturally led him to consider the Big Bang itself. If black holes informed our understanding of the fabric of space-time, then they could also offer clues about the first moments of existence. In 1971, Hawking put forth a radical idea that in the earliest epochs of the universe, a new type of black hole could have formed, not from the collapse of stars, but from the very birth of the cosmos itself. These were the so-called primordial black holes, a theoretical class of black holes that could have emerged in the first fractions of a second after the Big Bang. The story of the cosmos begins 13.8 billion years ago in an unimaginably hot and dense state. In its first instance, the universe was nothing more than a turbulent sea of energy fields, lacking the distinct forces we recognize today. As it cooled and expanded, these fields began to differentiate, giving rise to the fundamental forces that govern the universe: gravity, electromagnetism, and the nuclear interactions. With further cooling, the first subatomic particles, quarks and leptons, emerged, acquiring properties such as mass and charge. However, the universe remained far too hot and chaotic for stable atomic structures to form. Then came inflation, a brief but explosive period in which the universe expanded exponentially, doubling in size roughly 90 times in the span of 100 billionths of a second. This expansion magnified tiny quantum fluctuations into vast variations in the density of matter and energy, seeding the large-scale structure of the cosmos. Hawking saw an additional consequence of these fluctuations. Where there was excess density, there was increased gravity. As certain regions of the young universe became denser than their surroundings, their gravity caused them to collapse in upon themselves, triggering a runaway process that resulted in the formation of primordial black holes. These black holes would have been vastly different from those formed by collapsing stars. Instead of marking the end of stellar life cycles, they would have emerged at the very beginning of time. Their sizes would have depended on the moment of their formation. Those born earlier would have been minuscule, some no heavier than a paperclip, while those forming later could have rivaled the mass of thousands of suns. Mathematically, primordial black holes remain a compelling possibility. However, proving their existence is a far greater challenge. Unlike their stellar mass or supermassive counterparts, these ancient black holes would not necessarily be surrounded by accretion disks or emit detectable radiation. If they were formed in significant numbers, they could constitute a portion of dark matter, influencing the cosmos through their gravitational effects. Some have speculated that primordial black holes could explain mysterious astronomical phenomena, such as certain gravitational wave detections or even the formation of supermassive black holes in the early universe. Yet, detecting them remains a formidable task. When and where they formed, how numerous they were, and what sizes they likely reached are still open questions. The search for these ancient singularities is akin to seeking a needle in a cosmic haystack. But Hawking's legacy endures in the pursuit of these questions. His mathematics, elegant and unyielding, suggest that primordial black holes could very well have been among the first structures in the universe. The challenge now lies in proving it. As observational techniques advance, the possibility of detecting their subtle gravitational fingerprints grows ever more tantalizing. And so, the quest continues, not just to understand black holes, but to peer deeper into the earliest moments of the universe itself. What existed before atoms? If Hawking's vision was correct, then lurking in the fabric of the cosmos are remnants of a time before time, waiting to reveal the true origins of everything we see today. Finding the Needle. Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune, the 8 major planets of our solar system. Some have been observed since antiquity, their motions recorded by ancient astronomers who tracked their paths across the night sky with the naked eye. Others were discovered with telescopes, their existence predicted by the subtle gravitational tugs they exerted on their neighbors before finally being confirmed through direct observation. But even after 4,000 years of astronomical study, there are still unresolved mysteries lurking at the edge of our celestial neighborhood. One of them is the lingering possibility that yet another significant body remains hidden in the outer reaches of the solar system. In 1951, astronomer Gerard Kuiper pondered a fundamental question about comets. Scientists had long observed short-period comets, icy bodies that sweep through the solar system on highly elongated orbits, returning every 200 years or less. Halley's Comet, which last appeared in 1986 and will return in 2061, is among the most famous. Yet, every time such a comet passes near the Sun, it loses some of its icy mass to sublimation. Over time, these comets should have been completely depleted. Given the solar system's age, roughly 4.5 billion years, it seemed implausible that short-period comets could still exist unless there was a vast reservoir of icy bodies beyond Neptune, replenishing the cometary population. Kuiper proposed that such a belt of frozen objects must exist, periodically disturbed by gravitational interactions with Neptune and the other giant planets, sending some inward to become comets on their terminal trajectories toward the Sun. Yet, despite his hypothesis, it wasn't until 1992 that observational evidence confirmed its existence. After 5 years of searching beyond Neptune, astronomers detected the first Kuiper belt object. More soon followed, revealing a previously unknown population of icy bodies. But as astronomers cataloged more KBOs, an anomaly emerged. Some of these distant bodies followed highly unusual orbits. One such object, the dwarf planet Sedna, discovered in 2003, follows a long, elliptical orbit that takes over 10,000 years to complete. Even at its closest approach, Sedna remains more than twice as far from the Sun as Neptune, meaning that Neptune's gravitational influence alone cannot account for its extreme trajectory. Moreover, other trans-Neptunian objects display a striking clustering effect, aligning their orbits in a way that statistical models suggest should be random. Over hundreds of millions of years, their orbits should have scattered chaotically. The fact that they have not implies the presence of an unseen force shaping their motion. In 2012, Brazilian astronomer Rodney Gomes proposed a provocative solution, a distant, massive planet acting as a gravitational shepherd, exerting its influence from the solar system's outermost frontier. This theoretical world, dubbed Planet 9, would have a mass approximately 6 times that of Earth and follow an elongated orbit about 400 times farther from the Sun than Earth. Despite knowing where to search, however, astronomers have yet to detect Planet 9 directly. Some skeptics argue that the observed orbital anomalies are simply artifacts of observational bias. NASA's then chief scientist Jim Green, quoting Carl Sagan, cautioned, "Extraordinary claims require extraordinary evidence." And yet, the mystery persists. But what if Planet 9 is not a planet at all? What if it has all the mass and gravitational influence predicted by the orbital calculations, yet is something much smaller and much stranger, a primordial black hole? If such an object existed, its event horizon would be no larger than a tennis ball, making it effectively invisible against the vastness of space. It would not reflect light, nor emit detectable radiation in the visible spectrum, eluding even our most powerful telescopes. This might explain why it has remained undetected despite extensive searches. Detecting such a small but powerful object requires an entirely different approach. One possibility is that its intense gravity might attract a surrounding microhalo of dark matter. On a galactic scale, dark matter is thought to form vast halos around entire galaxies, helping to maintain their rotational structure. If a miniature version of this phenomenon surrounds a primordial black hole, then detecting the radiation from interacting dark matter could provide a means of identification. However, this method depends on the unresolved nature of dark matter itself. Despite comprising an estimated 27% of the universe's total mass energy content, outweighing normal matter 6-1, dark matter has never been directly observed. Its existence is inferred from its gravitational effects, yet no instrument has ever been able to detect it directly. Two competing hypotheses attempt to explain dark matter's composition. One suggests that it consists of weakly interacting massive particles, a class of theoretical subatomic particles that interact gravitationally but otherwise evade detection by existing physics models. The other posits the existence of massive astrophysical compact halo objects, which could include dense, invisible astronomical bodies such as black holes. Among the earliest proponents of the macho hypothesis was Stephen Hawking, who speculated that primordial black holes formed in the first moments of the universe could contribute significantly to the missing dark matter. If true, then the dark matter that binds galaxies together is not merely dark in the figurative sense, unknown and unseen, but dark in the literal sense, comprised of countless black holes formed in the first second of cosmic history. If primordial black holes are indeed abundant, then much of the matter that came into existence at the birth of the universe may have been instantly imprisoned behind event horizons, never to reemerge. Only a fraction, 1/6, by current estimates, escape this fate to form stars, planets, and the observable universe as we know it. The implications are profound. If Planet 9 is a primordial black hole, then it represents not just an anomaly in our solar system, but a window into the physics of the very early universe. Finding it would not only resolve a long-standing astronomical mystery, but also provide crucial insights into the origins of dark matter and the fundamental nature of space-time. So, how does one detect a black hole the size of a tennis ball hiding in the vastness of space? That is the challenge that now faces astronomers. Whether through indirect gravitational influences, interactions with dark matter, or novel detection techniques yet to be devised, the search for this missing piece of our cosmic puzzle continues. One fundamental concept in modern astrophysics relies on a prediction made by Stephen Hawking, Hawking radiation. This theoretical phenomenon, arising at the event horizon of black holes, is a product of quantum particle interactions subjected to the overarching framework of general relativity. According to Hawking's calculations, black holes are not entirely black, but rather emit a faint stream of radiation, akin to a gamma ray glow. Over vast timescales, this radiation leads to the gradual evaporation of black holes. Crucially, Hawking predicted that the smaller a black hole's event horizon, the more rapidly it will evaporate, culminating in an exponential increase in radiation that ultimately results in a catastrophic explosion. The implications of this theory are profound. If black holes with masses below kilograms had formed in the early universe, they would have decayed within a timescale shorter than the universe's current age. Consequently, astronomers have sought evidence of these theoretical remnants, scanning the cosmos for their final explosive emissions. The Fermi Gamma Ray Space Telescope, launched in 2008, has been one of the most sophisticated tools in this endeavor. However, after nearly 15 years of continuous observation, no definitive signals of such primordial black hole explosions have been detected. This absence of observational evidence serves as a critical constraint on the role of primordial black holes in the cosmos. Specifically, it suggests that less than 1% of dark matter can be attributed to these hypothetical entities. Such a result raises a tantalizing question: was Hawking's reconciliation of quantum mechanics and general relativity incorrect? The entire framework of Hawking radiation rests on intricate theoretical calculations, yet no empirical data has decisively confirmed its existence. Beyond direct gamma ray searches, astronomers have explored alternative detection methods rooted in gravitational effects. If primordial black holes were abundant, their gravitational influence would periodically distort the light from distant stars, a phenomenon known as gravitational microlensing. Likewise, gamma rays from pulsars or supernovae might flicker unpredictably if a primordial black hole passed between Earth and the source. However, exhaustive surveys in both optical and gamma ray astronomy have failed to produce compelling evidence of such events. These results impose additional constraints on the abundance of primordial black holes, particularly those with masses comparable to or smaller than Earth. Further indirect limits arise from astrophysical considerations. If primordial black holes were plentiful, they would occasionally capture and consume other dense objects, such as neutron stars and white dwarfs. The continued existence of these stellar remnants in large numbers suggests that such interactions have not been common, further restricting the possible prevalence of primordial black holes. Cosmologists have also turned their attention to the universe's earliest epochs in search of clues. If primordial black holes had formed shortly after the Big Bang, they would have influenced the distribution of matter in ways that should be imprinted in the cosmic microwave background. However, detailed analyses of the CMB have failed to reveal any such signatures for black holes in the mass range of 100 to 10,000 solar masses. If primordial black holes did exist, they must have been too small to leave detectable imprints on the primordial radiation field. For decades, these accumulating null results cast doubt on the viability of primordial black hole theory. However, in 2015, a breakthrough reignited interest in the idea. The Laser Interferometer Gravitational Wave Observatory detected the first ever direct observation of gravitational waves, traced back to the merger of two black holes, each with a mass approximately 30 times that of the Sun. This discovery confirmed the existence of gravitational waves, but also posed a perplexing astrophysical question: where did these black holes come from? Black holes of this mass are difficult to explain through conventional stellar evolution models. They are too large to be the remnants of typical star deaths, yet too small to be classified as supermassive black holes. One intriguing possibility is that they are, in fact, primordial black holes. If primordial black holes commonly formed with masses in the 30 solar mass range, their predicted collision rates align remarkably well with the frequency of black hole mergers observed by LIGO. While earlier observational constraints ruled out primordial black holes as the dominant component of dark matter, they did not exclude their existence altogether. Instead, they have refined our understanding, placing strict limits on the possible mass ranges in which these objects might exist. Interestingly, there remain unexplored mass regimes where primordial black holes could still play a crucial role in cosmic evolution. Simulations suggest that if dark matter were partially composed of primordial black holes with masses around 1.4 solar masses, they could have significantly influenced the formation of the first stars, galaxies, and even supermassive black holes. The question of primordial black holes remains one of the most compelling mysteries in modern cosmology. Future observational efforts hold the potential to unlock new insights. The James Webb Space Telescope, with its unparalleled ability to observe the earliest galaxies, may provide indirect evidence of primordial black hole seeding. Meanwhile, the Laser Interferometer Space Antenna, a next-generation space-based gravitational wave observatory set to launch in the 2030s, will be capable of detecting the signatures of black hole mergers at an unprecedented level of detail. Stephen Hawking's pioneering insights into black holes opened a new frontier in theoretical physics, and the search for primordial black holes continues to push the boundaries of our understanding. Whether they prove to be key players in the universe's earliest moments or remain elusive relics of theoretical physics, their study holds the potential to answer fundamental questions about dark matter, galaxy formation, and the very nature of space-time itself. The quest to uncover their secrets is, in essence, a quest to illuminate the deepest mysteries of the cosmos.